Okay, these are the answers to the chapters 1 through 3 practice test. And we're going to start with the multiple choice questions. Here we go. Number 1, which of the following processes requires a chemical change? 3 of these choices involve the separation of a mixture. 1 of these choices, which is the correct answer, involves not really separating, but more decomposing a compound, and that would involve a chemical change. So because salt water, air, and green ink are all mixtures, that's a physical change, but water is a compound that would require a chemical change to break it down. Correct answer is B. Number 2, which of the following statements is consistent with Thomson's and Millikan's work with cathode rays and electrons? So before we take a look at these 4 choices, let me go ahead and call your attention to page 42 in your textbook, and I'll highlight this sentence that says that J.J. Thomson observed that cathode rays are the same regardless of the identity of the cathode material. So it doesn't matter whether the cathode ray comes from hydrogen or helium, it's still going to have the same properties. As far as the second choice about are cathode rays attracted toward a negatively charged plate, no, that's incorrect. Since a cathode ray consists of negatively charged electrons, it would be attracted toward a positive plate. Now, as far as whether the answer is C or D, again, let's go back to the textbook. On pages 42 and 43, they talk about combining Thomson's work, which gave us the charge to mass ratio, and Millikan's work, which calculated the charge on the electron. We end up with the mass of an electron, which is about 2,000 times smaller than that of a hydrogen atom. So the correct answer to this question is C. In number 3, this is a pretty simple question. We know that iron has an atomic number of 26 on the periodic table. So it has 26 protons. It is a mass of 56. The mass number is the sum of the protons and neutrons. So 26 plus 30 is 56. And the charge is equal to the difference between protons and electrons. Since we have a positive 3 charge, that means that the neutral atom lost 3 electrons. So correct answer is 26 protons, 30 neutrons, and 23 electrons. Number 4, we have to work this calculation out to decide are these numbers in the correct positions. We start with the number of atoms of aluminum, so 2.0 times 10 to the 24. We're going to convert from atoms to moles, so we're going to use Avogadro's number to do that. Then we're going to convert from moles of aluminum into grams, and the periodic table tells us the molar mass of aluminum is 26.98. And then finally we're going to go from grams to milliliters, and we use density as a conversion factor, so putting grams on the bottom and 1 milliliter on top. We don't have to do the actual calculation, but we can see that to get the numbers in the proper positions, the correct answer that does this is D. All right, on to number 5. This gives us a mass spectrum of an unknown element. Each of those bars on that graph refer to a particular isotope of this element. So 90, 91, 92, 94, and 96 are the different isotopes that occur naturally. The height of that particular bar is going to tell us the relative abundance. So this is the data that we get from this graph. The most abundant isotope is mass number of 90. It's about 50%. 91 about 10%, 92 about just under 20%, and the same with 94. And there's a small little amount, maybe 2% is mass number of 96. So will these particular isotopes all average together to give us a mass number of 90? know, but it's going to probably fall somewhere between 90 and 92. So the correct answer to this question is D. In question number 6, we are given the empirical formula of compound X, and we have to determine the empirical formula of compound Y. Now, since each of these compounds has a different mass of carbon and hydrogen, the best way to solve this problem is to get the ratios to match, either having the same amount of carbon or the same amount of hydrogen. Then we can make an easier comparison. So what I did with these numbers for compound X is I simply multiplied them by 2. So now we have 6 grams of carbon and we have 0.5 grams of hydrogen. And now we can compare compound X and compound Y, and just focusing on the hydrogen, we see that the hydrogen to carbon ratio in compound Y is twice as much as that of compound X. So there must be twice as much hydrogen relative to a formula of CH. That means that the correct answer will have to be CH2. In number 7, we are given that boron 10 and boron 11 are the two naturally occurring isotopes. On the periodic table, we see that the average atomic mass of boron is 10.81. So this tells us that the relative abundance of boron 11 must be greater than that of boron 10, since 10.81 is closer to 11 than it is to 10. This means we can eliminate choice C. It cannot be a 50-50 mixture. And we can also eliminate choice D because it shows that there's a higher abundance of the lighter isotope. As far as whether the answer is A or B, let's take a look at the math, and we can see that even without a calculator, this is fairly simple math for us to do. Starting with choice B, that would be 10, the mass of the boron isotope, times the percent abundance as a decimal, so 0.4, plus the other isotope, 11, times its percent abundance. We get 4 plus 6.6. This is close but not correct. And then finally the correct answer, which is A, we're multiplying 10 times 0.2 plus 11 times 0.8, and we get 2 plus 8.8, which tells us that the correct answer is A. In number 8, we are given that the formula is either CrO, CrO2, CrO3, or Cr2O3, and we do have the mass percent of oxygen. So the only other element is chromium. There must be 52% chromium by mass and 48% oxygen. A 100-gram sample of this compound contains 52 grams of chromium and 48 grams of oxygen. Here's what we get off the periodic table. The molar mass of chromium is 52, and the molar mass of oxygen is 16. So 52 grams of chromium is exactly 1 mole, and 48 grams of oxygen atoms is exactly 3 moles. Therefore, since the ratio must be 1 to 3 between chromium and oxygen, the correct answer is C. In number 9, we are given some experimental data regarding a metal that's being heated in the presence of oxygen. So we start off with a metal, and then we turn this into a metal oxide. The mass of the metal is equal to 5 grams, and the mass of oxygen that combined with this metal is equal to 2 grams. So if we know that the ratio of oxygen to metal is 2 to 5, and of course we know that the atomic mass of oxygen is 16, let's multiply this ratio by 8. There must be 16 grams of oxygen for every 40 grams of metal. We'll go ahead and double that just to see what happens if there's 2 oxygen atoms in the formula. There would be 32 grams of oxygen for every 80 grams of metal. Now, the periodic table will tell us the molar mass of magnesium, calcium, potassium, and tin. And if you look at these numbers, the only choice that is going to give us a ratio that is either 16 grams of oxygen for every 40 grams of metal, or if we double it, 32 grams of oxygen for every 80 grams of metal, the correct answer must be B, calcium oxide, because that ratio is 16 grams of oxygen for every 40 grams of calcium. In number 10, all 4 of these compounds contain exactly 1 atom of oxygen, and it's asking for which of them contains the greatest mass of oxygen in a 1 gram sample. So the correct answer is going to be the substance that has the greatest percentage of oxygen by mass, and since all of them contain exactly 1 mole of oxygen, whichever substance has the smallest molar mass is going to be the one that has the largest percentage of oxygen by mass. So the correct answer in this case is B, magnesium oxide, because it has the smallest molar mass and the largest percentage of oxygen by mass. In number 11, we have an empirical formula of XF4, and we're trying to figure out the identity of X, or at least its atomic mass. The periodic table tells us that fluorine has an atomic mass of 19. And if we have 4 fluorines, that means we have a total mass of 4 times 19, which is 76. So there are 1.6 grams of X for every 3.8 grams of fluorine. This is the same as 16 grams of X for every 38 grams of fluorine. Let's go ahead and double that. There'd be 32 grams of X for every 76 grams of fluorine. So that means that the molar mass of element X must be 32. In number 12, we are given some combustion analysis data for a particular compound that contains carbon, hydrogen, and nitrogen. Since we don't know exactly how much nitrogen dioxide was produced, we can figure out the correct answer just based on the carbon and the hydrogen. All of the carbon that was originally present in this compound has now been converted into carbon dioxide. Because there's exactly 1 mole of carbon dioxide produced, that would equal 1 mole of carbon atoms from the original sample. Now the next math is a little trickier without a calculator. We have to convert 45 grams of water into moles. So think about the ratio. We're doing 45 divided by 18, the molar mass of water. 45 over 18 is the same as 5 over 2. So 2.5 moles of water has been produced, and that would be equal to not 2.5 moles of hydrogen atoms, but actually 5 moles of hydrogen atoms because of the subscript. There's actually twice as much hydrogen atoms as there are moles of water. Okay, so now that we know that the ratio of carbon to hydrogen in this mystery compound is 1 to 5, that means that the correct answer is B. In number 13, if you don't have a balanced chemical equation, you should probably write one to make sure that you know what the mole ratios are between different substances. So here we have the decomposition of potassium chlorate to produce potassium chloride, so KCl, and oxygen gas, O2. The balanced equation is 2 moles of potassium chlorate produce 2 moles of potassium chloride plus 3 moles of oxygen. The number 12.26 grams is a nice simple factor of 122.6, so we have 0.1 moles of potassium chlorate. This will produce 0.1 moles of potassium chloride. But the question is asking for about oxygen, how many grams of oxygen. First, we have to convert moles of potassium chlorate into moles of oxygen. And that is not a 1-to-1 ratio. It's actually a 3-to-2 ratio. So if you thought that 0.1 moles of oxygen was going to be produced, You probably didn't write yourself a balanced chemical equation, so let's convince ourselves that we actually produce 0.15 moles of oxygen. Now the last step in this conversion is to get to grams. You know that there are 32 grams of oxygen in 1 mole. That means that choice B represents 1/10 of a mole, which is incorrect. And choice D is twice as much, and that is also incorrect. The correct answer falls exactly halfway in between 3.2 and 6.4 grams. And so the correct answer is C, 4.8 grams of oxygen. In number 14, we have to convert from grams of one substance into molecules of another substance, but this time we do have a balanced chemical equation. We know that 18 grams of water is 1 mole, and we're converting from moles of water into moles of phosphorus pentachloride. This means we're going to divide by 4, and now we have to take 0.25 moles of phosphorus pentachloride and convert that into molecules. If we multiply by Avogadro's number, we get an answer which is 1.5 times 10 to the 23rd. Again, that's pretty simple mental math, and that you're taking 1/4 of the number 6, and the answer again is A. In number 15, we don't have a balanced chemical equation, so let's go ahead and write one. We're reacting potassium and chlorine to make potassium chloride. So you can think of this as potassium's molar mass is 39.1. That means there's 78.2 grams of potassium, and it's reacting with 70.9 grams of chlorine. Now the question said that equal masses of potassium and chlorine are combined together until either one or both of the reactants has been used up. Well, if we have equal masses, let's just make up a number. Let's say we have 78.2 grams of potassium and 78.2 grams of chlorine. Hopefully you can see that there's going to be some leftover chlorine at the end while all of the potassium is going to be consumed. So the correct answer is that you'll make product, potassium chloride, and you're going to have some leftover chlorine, so the correct answer is C. All right, number 16, we should write ourselves a balanced chemical equation between hydrogen and nitrogen to produce ammonia, NH3. And we have 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia. The molar mass of hydrogen is 2 grams per mole. So 3 moles of that would be 6 grams total. For nitrogen, 1 mole of nitrogen is going to have a mass of 28 grams, and 2 moles of ammonia at 17 grams per mole is going to give us 34 grams. Now we're not confirming the law of conservation of mass here, but it's kind of nice to know that 6 plus 28 equals 34. You might look at the problem and think that 3 grams of hydrogen plus 7 grams of nitrogen is going to make 10 grams of product, but we have to consider that if there's a limiting reactant, there's going to be some leftover or excess of another reactant. As far as determining the limiting reactant, let's take these numbers, 6, 28, and 34. Let's go ahead and cut these numbers in half. So 3 grams of hydrogen would react with 14 grams of nitrogen. Do I have 14 grams of nitrogen available? No. So that means that nitrogen is the limiting reactant because I only have 7 grams available. So since nitrogen is a limiting reactant, the answer must be either C or D. If we cut those numbers in half one more time, 1.5 grams of hydrogen will react with 7 grams of nitrogen. And since all of the nitrogen reacts, but only half of the amount of available hydrogen reacts, there's going to be 1.5 grams of hydrogen left over at the end, and our theoretical yield of ammonia is only 8.5 grams. In question 17, it's about chromatography, and we have a difference in polarity. So the correct answer is going to be either C or D. It's not about molar mass, it's about polarity. Now, the fact that the solvent is polar, whichever component ran the fastest up the filter paper must mix better and more efficiently with the solvent, which is the mobile phase that's running up the paper. So since component A runs up the paper more quickly than component B, component A must be able to interact more easily with the polar solvent. Also, if something doesn't move very fast, it has to do with its potential interaction with the paper itself. And since the surface of the paper is coated with a non-polar substance, then component B must be able to interact more easily with that non-polar paper surface, and that's why it moves more slowly. Therefore, A is more polar than B. In number 18, this seems like a very confusing question because you might not really even understand how you're supposed to distinguish between something called molecular vibration, molecular rotation, and electron transition. I'm going to quote a particular section of the AP curriculum. This is the guide that is given to teachers to make sure that we know what topics we're supposed to cover. And here is a section that deals with the interaction of radiation or electromagnetic waves with matter. It talks about the energy of a photon related to its frequency, and it also mentions that different types of molecular motion lead to absorption or emission of photons in different spectral regions. One spectral region is infrared. Infrared radiation is associated with transitions in molecular vibrations. That's something that AP chemistry students should know. And it goes on to say that ultraviolet or visible radiation is associated with transitions in electronic energy levels. So what I can infer from this is that there are two different types of radiation. The one that has higher energy would be the ultraviolet or the visible. The one that has lower energy is infrared. So if that's true, then molecular vibration requires less energy. Electronic transition requires more energy. So the amount of energy required to make a molecule vibrate its bonds is less. The amount of energy required to excite an electron up to a higher energy level is more. So we're looking for either ultraviolet or visible for the electronic transition, and we're looking for infrared radiation for the vibration. Let's go back to the question. So we have molecular vibration in region Y, where it says infrared. We have electronic transition in region X, where it says ultraviolet and visible. And there must be something even lower than infrared in the microwave region. Whatever that is, it must be something that requires even less energy. So because electronic transition has to be region X, we know that the correct answer is either B or D. Because molecular vibration has to be region Y, the correct answer is D. And apparently it takes even less energy just to simply rotate a molecule in space than it does to stretch or vibrate those bonds. Okay, correct answer is D. And now we're ready to move on to the free response questions. Number 1 is just a table to fill in. So you have your periodic table that will tell you the number of protons for indium and for phosphorus. You can also figure out what the symbol of an element who has 35 protons is. That's going to be bromine. And 56 protons, that's going to be barium. The first column is just the charge that we have to fill in here. So that's going to be +3 for the indium ion, -3 for the phosphorus ion. The next one, the charge has to be -1 because we have an extra electron. And the last one, the charge has to be positive 2 because we have lost 2 electrons. So indium has atomic number 49 protons. Phosphorus has atomic number 15 protons. 115 is equal to the sum of the protons and neutrons. So 49 plus 66 is 115. 15 plus 17 is 32. For the indium to have a plus 3 charge, it must have lost 3 electrons. And for the phosphorus to have a negative 3 charge, it must have gained 3 electrons. Again, I said that 35 was the atomic number of bromine. This is bromine with a negative 1 charge, and it has a mass of 35 plus 45, which is 80. So 80 is the mass number, and the charge is negative 1. And then 56 corresponds to barium. It has a mass number of 56 plus 81, which is 137, and it carries a plus 2 charge. For question 2, we have to go from name to formula and then decide if it's ionic or covalent. The symbol for cobalt is capital C, lowercase o. The symbol for carbonate is CO3, capital C, capital O. The carbonate is negative 2, and therefore, since cobalt has a positive 2 charge, you would simply write CoCO3. This is an ionic compound because it involves ions, metal and nonmetal typically. Barium is Ba with a plus 2 charge. Chlorate is ClO3, but it has a minus 1 charge. So we need 2 chlorate ions in this formula to balance the charge. Again, it's ionic because it contains ions. The next one is a covalent compound, and you can tell because of the prefixes. So we're simply naming the compound dinitrogen trioxide, and that refers to the number of atoms of nitrogen and oxygen. N2O3, it's covalent. The next one is ammonium, which is a cation, NH4, and phosphate, the anion, is PO4. The charge on ammonium is plus 1. The charge on phosphate is minus 3. So it takes 3 ammonium ions to balance the charge on 1 phosphate. Even though there's no metal in this compound, it is still considered to be ionic because it contains cations and anions. The last compound is sulfur tetrafluoride. We're just simply counting how many atoms we have. The formula is SF4, and it is covalent because it involves 2 nonmetals. In question 3, now we have to go from formula to name, as well as determine whether it's ionic or covalent. Our first example is covalent because both chlorine and oxygen are nonmetals. We name it using the prefixes di and hepta. So we have dichlorine heptaoxide, which is covalent. Our next substance is ionic. Magnesium does not require a Roman numeral because it's always plus 2. NO3 is called nitrate, so we simply call it magnesium nitrate, and again it's ionic because it contains ions. Our next one is potassium sulfide. It is ionic, therefore we do not have to use prefixes. Potassium does not need a Roman numeral. It's just going to be called potassium sulfide. And again, it's ionic because it contains ions. Phosphorus and bromine are nonmetals. This is a covalent compound which we now can use prefixes. So phosphorus pentabromide is covalent. Our last one is ionic. Copper is a transition metal which can have multiple possible positive charges, different oxidation states. Therefore, we have to put a Roman numeral with the name copper. Acetate is -1. Because there are 2 of them, that means the charge on copper is plus 2. So copper, Roman numeral 2, acetate, and again it's ionic because it contains ions. In number 4, we're going to be given some combustion analysis data, and we have to determine the empirical formula. It contains carbon, hydrogen, nitrogen, and oxygen. If we can figure out how much carbon, hydrogen and nitrogen there are in this compound, then we can subtract those masses from the original mass of the compound to determine the amount of oxygen that's present. We'll start with the carbon. 6.8618 is the number of grams of carbon dioxide that's produced. Let's convert this into grams of carbon using the atomic mass of carbon and the molar mass of carbon dioxide. And we get 1.8725 grams of carbon. I'm keeping the number of significant figures consistent, so therefore, since there were 5 sig figs in the given mass of carbon dioxide, I have 5 sig figs in my answer. For part B, it's very much the same, but watch out for the fact that there are 2 hydrogens in water. So therefore, the molar mass of 2 moles of hydrogen is actually 2.016 grams, and therefore you get, as your conversion is complete, 0.19646. Again, notice that I have 5 significant figures in my answer. In part C, we are not given the amount of nitrogen dioxide that was produced. We're simply given the mass percent of nitrogen in the original compound. This is a very easy calculation. We're just simply going to multiply the mass of the compound by the percent nitrogen as a decimal. So we get 0.5462 grams of nitrogen, and I have 4 sig figs in my answer because the percent had 4 sig figs. Now we're just going to subtract everything we know from parts A, B, and C. We're going to subtract those from the mass of the compound itself. So 3.8625 minus the mass of carbon minus the mass of hydrogen minus the mass of nitrogen gives us an answer of 1.2473. And the rule for subtracting is you go with the least number of decimal places. So I'm going to go with 4 decimal places in this case. And now that I know the mass of each of the 4 elements, I'm going to be able to determine the empirical formula. Here are the numbers in terms of their grams. I'm going to go ahead and divide each of these by their respective atomic masses. So divided by 12.01 for carbon. Now again, even though hydrogen gas and nitrogen gas and oxygen gas are diatomic, these aren't going to be doubled because we're just talking about the amount of each element as it appears in the compound. So we're not using the diatomic molar masses. We don't deal with hydrogen gas or nitrogen gas. We're just talking about the individual elemental analysis. If you do this math, these are the numbers you get. The next thing for us to do is to divide all of these numbers by the smaller. The smallest amount in this case is 0.03899. So we divide each and every number by that particular value. And we get really close to a whole number. With carbon, hydrogen, and oxygen, of course, we get exactly 1 with nitrogen. So because of this data, therefore, the empirical formula of the compound is C4H5NO2. Part F is asking us to calculate the molar mass of this compound, and we are given that 8.65 grams of the compound contains 1.75 times 10 to the 22nd molecules. The units of molar mass are not grams per molecule, but rather grams per mole. So how do we get rid of the molecules? Well, just use Avogadro's number. And since Avogadro's number has units of molecules per mole, we're going to get grams per mole in our answer. If we do this math, we get 298 grams per mole. And then finally, determining the molecular formula of the compound, let's go back to the empirical formula. C4H5NO2 has a molar mass of 99.09 grams per mole. 298 is obviously the molar mass of the real compound. 99.09 is the empirical formula's mass. Since the molecular formula is always a multiple of the empirical formula, even when that multiple happens to be 1, we're going to divide the molar mass by the empirical formula mass. In this case, we get 3, so therefore C4 now becomes C12. H5 now becomes H15, and NO2 now becomes N3O6. In question 5, this is going to be a limiting reactant problem. So we have to determine the number of moles of each reactant. The equation has already been balanced for us. The way we get moles of pentanols, we have to go from milliliters to grams, and then from grams to moles. So to go from milliliters to grams, we're going to use the density as a conversion factor. 1 milliliter on the bottom, 0.814 grams of pentanol on the top. And then to go from grams to moles, we put the molar mass of pentanol, C5H12O, on the bottom, and then 1 mole on top. So that calculation gives us 0.0679 moles of pentanol, and I rounded off my answer to 3 significant figures based on the volume. For moles of oxygen, we go from liters to grams using density again. So 1 liter on the bottom, 0.922 grams on the top. We convert from grams to moles using the periodic table, and that calculation gives us 0.461 moles of oxygen, again 3 sig figs based on the volume. Now the limiting reactant is not necessarily the pentanol just because there is a smaller number of moles. We have to consider the balanced equation in which 2 moles of pentanol react with 15 moles of oxygen to produce 10 moles of carbon dioxide and 12 moles of water. One way to determine the limiting reactant is to convert each reactant into product. I'm just going to pick CO2 as a product because it's the first one listed, and also because I'm going to need the theoretical yield of carbon dioxide eventually. So I take my numbers from parts A, 1 and 2. I use the stoichiometry, which is the mole ratio, to go from moles of pentanol to moles of carbon dioxide. That's a 10 to 2 ratio, and I get an answer. I do the same thing with oxygen, but this time the ratio is 10 moles of CO2 for every 15 moles of oxygen, and I get a different number. Now because the number of moles of carbon dioxide product is smaller coming from oxygen, that is one way to prove that the limiting reactant is oxygen, because it produces a smaller amount of product than the other reactant does. Another way you could have answered this question is you could have converted one reactant into another. It would look something like this. So I'm going to go ahead and take the moles of pentanol and convert that into moles of oxygen using the 15 to 2 ratio from the balanced equation. Now I get an answer of 0.509 moles of oxygen that are required to react with all of the pentanol. Well, the problem is I only have 0.461 moles of oxygen available. So the limiting reactant is oxygen because the amount of oxygen that I need for complete reaction with the pentanol is greater than the amount of oxygen that I actually have available. So this is another way to prove that oxygen is limiting. All right, on to part C. Calculate the theoretical yield of carbon dioxide in grams. If we go back to an earlier calculation that came from oxygen, 0.307 moles of carbon dioxide would come from the oxygen in the calculation. All we have to do is convert that to grams. There's 44.01 grams of carbon dioxide per mole. So we get a theoretical yield of 13.5 grams of carbon dioxide. That's 3 significant figures based on what I initially had to begin with. The percent yield is calculated like this. It's actual yield divided by theoretical yield, and then times 100. So in this case, we have 11.0 divided by 13.5, and we get a percent yield that is around 81.5%. Okay, last problem. This is sort of like an empirical formula. It's actually a mole ratio between water and a particular anhydrous salt. But as far as mole ratios are concerned, it's pretty similar, where all you have to do is figure out the moles of barium hydroxide, the moles of water, and then you're going to find that mole ratio. Let's get started. Part A is asking us to calculate the mass of the hydrate sample. That is an easy calculation. Just subtract those two numbers, and we get 4.224 grams of the hydrate that was present in the crucible before it was heated. Now, the balanced chemical equation for the reaction between barium hydroxide and sodium sulfate looks like this. It's a double replacement, so we get barium sulfate and sodium hydroxide. And there should be a coefficient of 2 in front of the sodium hydroxide. In terms of the conversion from grams to moles, 3.126 grams of barium sulfate converted into moles gives us 0.01339 moles of barium sulfate. Now look at that 1-to-1 mole ratio between barium sulfate and barium hydroxide. That means that there's 0.01339 moles of barium hydroxide. Let's convert that to grams. And when we do, we get 2.294 grams of the anhydrous salt barium hydroxide. You recall that in part A, the mass of the hydrate was 4.224 grams. We just calculated that the mass of the anhydrous salt is 2.294 grams. That difference tells us how much water was lost whenever it was heated. And that is equal to 1.930 grams of water. All we have to do now is convert grams of water into moles and then find the mole ratio between water and barium hydroxide. So 1.930 grams of water converted into moles is equal to 0.1071. That's how many moles of water was lost in the heating process. Remember that the moles of the anhydrous salt from part D is 0.01339. Let's calculate this mole ratio because the value of X is equal to the ratio of moles of water divided by moles of the anhydrous salt. And that's going to give us 8, which means that the original hydrate had an 8 in its formula. It would have been called barium hydroxide octahydrate. Well, that last calculation concludes the chapter 1 through 3 practice test. I hope that my answers and explanations were helpful to you. Good luck studying for your test.